In this problem, I'm given a force function for the force on a particle, and I'm trying to relate that to the potential energy function and then look at equilibrium points. So I want to point out at first that this periodic force function has a period of 2 pi over the coefficient of x, or 2 pi over k. And the way to think of that is that the period would be the value of x I plug in to get a 2 pi out of the argument of the cosine function, thereby guaranteeing that it's just completed its first wiggle. So replacing x with 2 pi over k, I would indeed get a 2 pi. Okay, so there's that, and it should be useful later. So how do I get the potential energy function? I use the fact that the force function is the negative derivative of the potential energy function. If I indulge in some formality here, I can solve for du and say that it's negative f of x dx. If you like, you could just guess an antiderivative, but I wanted to make an integral sign, so here we go. Okay, finding antiderivatives on both sides, I have that u of x is the negative antiderivative of f of x, and that would be a negative a over k because of dealing with the chain rule backwards, sine kx plus an arbitrary constant. And this is a good reminder that potential energy functions come with that flexibility of an arbitrary constant. We see it with conservation of energy problems with gravity, that it doesn't matter where you define y equals 0. And that's because potential energy functions have this flexibility of shifting the origin up or down without changing the physics. Okay, so there's our potential energy function. Now I want to get the equilibrium points on this interval, and the interval I gave was exactly the first period of this function. So let's pop in just a qualitative graph of the potential energy function. Okay, there's my potential energy function. It's just a generic upside down sine function with a period of 2 pi over k. And equilibrium points are going to occur where there's a local extremum of my potential energy function. So at those points, I have a horizontal tangent. And I don't have to do any calculus to find out the x locations here. Here's half a period where the function crosses the x-axis. And my first equilibrium occurs at a quarter of a period, which would be 2 pi over 4k, or pi over 2k. My next equilibrium occurs at 3/4 of a period. So that would be, just scratching it out real quick, 3/4 of a period. That would be 3 pi over 2k. And then I want to classify these equilibrium points. Well, when I have a local minimum, that's a stable equilibrium. So this one is stable. When I have a local maximum, that's unstable. And just a quick reminder of why. So if I go just a small distance away from that stable equilibrium point, the slope of my potential energy function is positive, but that means if I go back to the relationship between force and potential energy, that means my force is negative, which points back toward the equilibrium position. So if the particle is here, it experiences a leftward force. If I displace a little bit to the left of that stable equilibrium, the slope of my potential energy function is negative, which means the force is positive, and again points back toward that equilibrium position. So this is where an object could wiggle back and forth. The other one is unstable because if I displace a little bit from that equilibrium position, the slope of the potential energy function is negative, which means the force is positive, pointing away from the equilibrium point. So a small displacement of the object would result in the object running away from that equilibrium point. Similar if I displace a little bit to the left. So the last thing I wanted to do here is put a graph of the force function in right next to this potential energy function, and we can look at the equilibria from that perspective instead. Okay, here's my force function. And instead of talking about an equilibrium as a local min or a local max, an equilibrium is a place where the force is equal to 0. So that's going to occur, of course, at the local extrema of the potential energy function where the slope is equal to 0. So I have force equals 0 at pi over 2k. And again at 3 pi over 2k. And at this first point, I imagine a small displacement to the left of the equilibrium point. And I see that the force is going to be positive. So if my particle is here, it experiences a positive force. A small displacement to the right, well, my force value is negative. So displacing to the right means the force points back to the left. So I can tell from this picture also that this is a stable equilibrium. If I do a similar thing with the other equilibrium point, if I displace to the left of it, the value of F is negative. That means force points to the left, away from the equilibrium point, and similar for pointing to the right if I displace slightly to the right of that equilibrium point. So that one is unstable.